Hey all, so this is the Exam 2 review for Math 116. And so the first section is section 2.1, quadratic equations. And this is where we're solving them. We have a few different methods for doing that. In general, we're going to want to get to standard form, which is this ax squared plus bx plus c. Kind of no matter where we're starting from, that's where we're trying to get to. And then once we get to here, we can determine which of the methods we want to use. So with factoring, we're just going to basically factor with it set to 0 and then solve each of the factors to 0. Square root property, this one comes up occasionally. If I have something in the form chunk squared equals a number, I can root both sides and solve. So that's another way, but this one's a little bit limited, but when it's useful, it's pretty good. And then quadratic formula is when it doesn't factor or when it's going to be really terrible to factor. And we're in standard form, we can just throw it right in the quadratic, and then that's going to get us our solutions. So let's see what some of those look like. Okay, so this first one isn't in the best form. We need it in standard form, so I'm going to have to FOIL this and then bring this side over and get it incorporated so I can get it to 0. And then once we get it to there, then we can see which of the three methods it makes sense to use to solve it. So foiling, I get x squared, and then outside I get minus 5x, inside I get 4x, and then minus 20, and that equals 2x minus 2. Let me go ahead and collect here first. X squared, so minus 5 plus 4 is going to make minus x, and then minus 20 equals 2x minus 2. So then from there, I'm going to bring these over to this side. So since I have a plus 2x, I'll minus 2x. And minus 2, so I'll plus 2. So I'm trying to make this side 0. And now I have x squared minus 3x and minus 18 equals 0. So at this point, this is where I would go. Does it factor? If so, that's going to be the easiest way to do it. Or do I need to use the quadratic formula? And so in this case, are there two numbers to multiply negative 18, add to negative 3? Yeah, negative 6 and 3. So I can do x minus 6, x plus 3 equals 0. So then those are the factors. So remember, the zeros have the opposite signs because we're setting this to 0 and bringing the 6 over. So it makes x is 6 or x is negative 3. For number 2, again, it's not in this form that we want. So this one has a fraction in it. So what I'm going to do first is I'm going to multiply both sides by x, because that's my denominator. And then that's going to clear the fraction. So here I'll have x times x is x squared. Here x over x would just cancel, leaving me just the plus 36. I have to do the same thing to this side. So that makes a 13x over there. Now that I don't have fractions, I'll get this 13x over to the other side by subtracting. And I'll write it in descending order. So x squared minus 13x plus 36 makes 0. And then we're doing the same thing we did here. Is there anything that multiplies at 36 and adds to be negative 13? Yep, and that would be x minus 4 and x minus 9. And now, so those are my factors, so my zeros are going to be positive 4 and positive 9. And again, the way that I'm getting that, the reason the signs are opposite, is because I'm just setting that to 0 and adding the 9 to both sides. So either way, if this is plus, I'm subtracting, so it's opposite, minus, it's plus. So that's why these have opposite signs. For number 3, let me write it a little bit bigger right here. So this is one that's of the form, bring this back, something squared equals a number. So I have a chunk of math squared equals a number. So I can just square root both sides. I just have to remember to use the plus minus. So this is the case. Again, it's limited, but when it works, the square root property is handy. So we'll do that, and we'll do that. So square root undoes square, and I just have x minus 7, and then equals plus or minus. Square root 25 is 5. So then I can add my 7 over. So that means I have x equals 7 and then plus or minus 5. Since this is plus or minus 5, that means it's really 7 plus 5. So in that case, x would equal 12, or 7 minus 5. And then in that case, equal 2. Okay, so number 4, this one has the fractions again. And so I'm going to clear those because I could put the fractions in the quadratic formula, but that sounds kind of miserable. So instead, I'm just going to make them all whole numbers. So if I multiply this side by 8, I have to multiply that side by 8. In this case, it won't matter because it's times 0, but we do have to do the same thing to both sides. And so here we got 8 over 8 cancels, so that's going to be an x squared. Here we'd have 8 over 2, so it'd be 8x over 2. 2 goes into 8 4 times, so minus 4x. And then 8 times 4, a lot of times people forget to do the whole number. Minus 32, and again 0 times 8 is still just 0. And same spot, so is there anything that multiplies to be negative 32 and adds to be negative 4? And there is, so that's going to go x minus 8 and x plus 4. So our zeros are, our solutions, 8 and negative 4. Number 5, so this one's already in standard form, and this is where we're going, is there anything that multiplies to negative 3 and adds to be 8? And it's like, no. So that's where you need to do the quadratic formula. So quadratic formula again, I'll just write it over here since it'll be bigger. X equals negative b plus or minus b squared minus 4ac all over 2a. And so in this case, my a is 1. It's the invisible 1 in front of the x squared. My b is 8, and my c is negative 3. And I'm just going to take these, put them in here, and grind out the math. Okay, so that will be x equals negative 8, so 8 going in for b, plus or minus 8 squared minus 4. A is 1, and c is negative 3. And then all over 2a, so a is 1 again. And then x equals negative 8, plus or minus, that would go 64, minus and minus makes plus 12 over 2. X equals negative 8 plus or minus, that would be 76 over 2. And then 76, unfortunately, is 4 times 19, so I can simplify that a little bit. So that'd be x equals negative 8 plus or minus, square root 4 makes it 2 come out, and then the 19 stays inside. So I'm thinking of this as square root 4, square root 19, and that makes 2, and then 19. And that is over 2. And then once you do that bit of reducing, if there's a number here, here, and here, if all of those are divisible by the same thing, then that means it can be reduced. In this case, 2 goes into everything. So x would equal 2 goes into 8 4 times, 2 goes into 2 once, so I can just call that root 19, and then 2 goes into 2 once. So it's like I'm kind of thinking of it almost as 2 separate fractions, reducing that down to negative 4, and that becomes the invisible 1. Okay, so number 6 is pretty much what I just did, but with some words. So a tennis ball is thrown in the air from the top of a hotel that's 100 feet off above the ground. The height of the ball from the ground is given by that equation, where t is in time, in seconds after the ball is thrown. How long after the ball is thrown does it hit the ground? So this equation for hitting the ground, that would be at a distance of 0. Because we're starting off at the 100 feet off the ground. They're going to throw this ball, and then this is where 100 would be my scale, and then ground level would be 0. So basically I just have to set this equation to 0 and then solve that. So if I do that, my a is negative 16, my b is 96, and my c is 100. And there's a few things I could do. I could divide out at least a 2, maybe not actually a 4, I think, and make these numbers a little bit smaller. I could also multiply to make this positive, which gets rid of one sign. But I think probably what most folks would do is just toss it in the quadratic formula it is. In this case, we're going to be looking for decimals very likely. So I would just kind of use the numbers as they are, even though they're sort of horrible. So we're going to have t equals, and I'm writing t instead of x because t's are variable this time, it's time. Negative b, so negative 96 plus or minus 96 squared minus 4, and then a is negative 16, and for ac, c is 100. And that is all over 2a. And now we just have to kind of do the math. So t equals negative 96 plus or minus. I threw all that in a calculator. Notice minus and minus would make plus. And so then I got 10,816 over negative 32. So then I took the square root of that. Negative 96 plus or minus 104 over negative 32. And then that makes our kind of two answers. T can equal negative 96 plus 104 over negative 32, or t can equal negative 96 minus 104 over negative 32. Okay, so then this top one, this would become negative 96 plus 104 would be 8 over negative 32. And that's a negative time, so that doesn't make sense for an answer. That's like if we threw the ball from the ground and it followed the same parabola, that time would be back here. So that one is extraneous. And then this I just threw in the calculator, and I got t to equal 6.25. Okay, next section is 2.2 quadratic functions, parabolas. So this is looking more at the graphing and the vertex of the parabolas, whereas the last section was essentially just finding x-intercepts. That's what we did that whole time, because the y was 0, and we were solving for x. So in 2.2 we got two forms. Standard form, which is what we're mostly going to stick with, and then there's also another one called vertex form. Standard form, this is really our workhorse. So when we're in standard form, if we want to find the vertex, remember the vertex is like the bottom, or if the graph is opening this way, the top of the graph. To find the x-coordinate of that, we just do negative b over 2a, just like the first part of the quadratic formula. Once we know what x is, we just plug it back in, and that gets us our y. And that will give us the location of that point, which is going to be our maxes and mins when we get to the next section. Vertex form, I'm not going to have anything on my exam that involves vertex form. I'm going to do the first example anyhow, which is what I wouldn't put on mine. And the reason is sometimes other people use my notes. And so if other instructors are using these, they may want to include that in theirs. I choose not to. Okay, so this is the one that's like vertex form with what's called transformations. And so we just don't have enough practice for transformations to actually be very good at it. So like I said, this won't be on my exam, but if you have someone else teaching this course and you're using this video as a supplement, they may have it on there. So I just wanted to make sure I covered it. So if you did do transformations, then hopefully you remember that when we have plus and minus on the inside, that's our left-right shift. And plus, they go opposite the way you would think. Plus is going to shift left. So this one is going to shift left 3 because of that inside. And then if it had been minus, it would have gone right. And then on the outside, that's our up-down shift, and that one makes sense. Minus goes down, plus goes up. So this one's going to go down 5. And so our new vertex, instead of being at 0, 0, is left 3 and then down 5. And so that's how it's shifted, and then B is graph it. Well, I kind of started doing that over here. If you think about just x squared, y equals x squared, xy. If x is negative 1 squared is 1. If it's 0, it's 0. If it's 1, it's 1. So usually it looks like that u right here. And all that happened with this shift is it took this point, moved it 3 to the left and 5 down. So it's still going to just like go over 1, up 1, just like it did here. It's just going to do it starting down there. So again, if you're in my class, don't worry about that too much. But someone else's, again, that may be fair game. Okay, for number 2, determine whether the function's vertex is a max or a min. And this one is one that if you're in my class, you should definitely worry about. So if it's going to be a maximum, the parabola is going to be opening down, and that's going to make the vertex at the top, which makes it a max. If the parabola is opening up, then the minimum, it would be a minimum because the vertex is at the bottom. And we have maximums, or we have parabolas opening down, we have negative x squared, and we'd have minimums when the parabola is opening up, which means we have positive x squareds. So this one, since it's a negative x squared, that means that we're going to have a maximum. Find the coordinates of this point. So that goes back to here, and we're in standard form right now, so we'll just throw it in for negative b over 2a. That will give us x, and then plugging that back in will give us y. So x coordinate of the vertex equals negative b, so it's going to be negative of 6 over 2a, and a is negative 1. So negative 6 over negative 2 would make positive 3. And then once I have this, then I just plug that back in for x and I get y. So y equals negative of 3 squared plus 6 times 3 minus 5. Or y equals, that would be negative 9, because that negative isn't squared, only the number is. It's not negative 3 squared. Plus 18 minus 5. So down 14, up 18 would be 4. So my vertex is at 3 and then 4. Okay, so same question just continues. Find the zeros, so that's the same thing as find the x-intercepts. And then if it doesn't exist, say so. And the way it cannot exist is, say I have a parabola that's opening up here, or a parabola that's opening down here. There's no x-intercepts, it's never going to cross the axis. And so that can absolutely happen, so that's what the DNE is. And if you go to solve that, and you're solving and you get a negative under the radical and you're getting imaginary numbers, that means you have this case. So for this one, let me just grab the equation from the last page. And so what I'll do is, I'm going to multiply both sides by negative 1, just because I don't like factoring with a negative leading term. I think it makes it harder. So negative 1 on both sides. And that makes this still 0. But now it's x squared minus 6x plus 5. And I have a much easier time getting my head around what multiplies to 5 and adds to be negative 6 if I don't have to do it with sort of the double negatives and the sign's funky. So this will be x minus 1, x minus 5. So x equals 1 or x equals 5. So in terms of the graphing that's coming up, that isn't 1, 5, which sometimes people do. This is 1, y is 0. This is 5, y is also 0. So that's what it looks like in ordered pairs. Find the y-intercept. So we let y equal 0 to find the x-intercept. So now we're going to let x equal 0 to find the y-intercept. So that'll be y equals negative of 0 squared plus 6 times 0 minus 5. So it's always going to be the thing on the end. Y equals negative 5. And so again, as an ordered pair, when x was 0, y was negative 5. And now we're supposed to sketch this graph. So from the last page, we had a vertex at 3, 4. So x is 3, y is 4. We have x-intercepts at 1, 0, and 5, 0. And we have a y-intercept down here at negative 5. And so you can kind of see that's making a nice parabola. And we'll just connect that with a smooth curve. And that'd be our graph. Okay, so number 3 is average rate of change. And so over here I just wrote average rate of change equals, this is the formula on the interval a comma b. And so on the exam, if this isn't on the sheet of notes, I can't remember. I think on this one I put it right in the directions of the question to sort of help you know what formula we're talking about. We didn't do a ton of work with this, but it's not a terribly hard problem. So this is going to look like f of 4, so this is like my a and this is my b. So f of 4 minus f of 1 over 4 minus 1. And so now we're just plugging these in for x. And we can go, this equals f of x. We'll just go negative of 4 squared plus 2 times 4 plus 3. So that is f of 4. Then we subtract from that f of 1. And good to use these brackets. Just make f of 4 a number, make f of 1 a number, and then subtract them. A lot of times people drop the parentheses too early and don't get the minus sign distributed right. So if you just make them both numbers and subtract, you'll be totally good. So here we got negative 1 squared plus 2 times 1 plus 3. And that's over 4 minus 1, so that's just 3. So up front we got negative 16 plus 8 plus 3 minus, remember that negative's not squared, so negative 1 plus 2 plus 3, still over 3. So that would be negative 16 and 11, so negative 5, and then minus negative 1 plus 5, so that's 4 over 3. So negative 5 minus 4, negative 9. And it's just keeping track of all the signs over 3. So my average rate of change is 3. Okay, so this first example, if a company has a total cost of that and total revenues given by that function, find the break-even point. So back here, the equilibrium point or the break-even point, same thing, is where revenue equals cost. So we just have to set these two functions equal to each other and then solve. And so if we're solving means we're using quadratic equation. So doing cost equals revenue, so C of x equals R of x. I'll just take this one, 2400. And then once I do that, I want to get everything over to one side. I think I'm going to solve in the direction where I get a positive x squared. So I'm going to go minus 495 and plus. And I'll do the same thing on this side. And then that makes this side 0. And then this side I'll write in descending order. So 0.2x squared and 0.8x squared will just make x squared, because that would make a 1x squared. And then 35 minus the 495, so it's going to be negative 460x, and then to 24,000. And so it may be this factors, but it doesn't look that fun to factor. So I'm just going to toss it in the quadratic. But you could probably, yeah, you would be able to factor it if you tried. X equals, I'm just going to do negative is going to be positive 460 plus or minus negative 460 quantity squared minus 4, a is 1, c is a 24,000, all over 2a. And then at that point I would have busted out my calculator and made this a big number. If you're putting that in, it should be 115600 over 2. And I took the square root of that, so that got me 460 plus or minus, oops, no more square root, 340 over 2. And then I did 460 plus 340 divided by 2, and then the same thing with the minus. Which I've done a couple of times in the video already, so I'll just skip down to the answers. So that would be 400, and then the second answer is 60 when we do the minus. So these are the two values, number of units produced, that would be break even. Okay, for number 2, it's find the maximum revenue for the revenue function, this round or answer nearest cent. So if we're doing maximums or minimums, that's going to be vertex, because if you think about, like, if a parabola has a maximum, and like in this case it's going to be a parabola opening down, and that vertex is going to be the maximum point. The x is going to be the number of units that maximizes the revenue, and then the y in this case, which is the revenue, is going to be the actual revenue, the dollars. So you have to be a little bit careful when you're reading this as to which thing it's asking for. And it can even get a little more complicated than that, but I'll show that in some later examples. So remember, if we're doing vertex, it's x equals negative b over 2a. Once I get this, I plug that back in. And again, this is my units on this side. And then do the calculation. And when I get out the R, that's dollars. So that's the actual money. So units that will maximize revenue, and then what the maximum revenue is. So we just have to basically do this with that. So negative b, that's our 383 over 2, and then negative 0.6. And then I threw that in the calculator, and then I got this kind of ugly number. And so that's just, that decimal goes on forever. So what I would have done then is just, typed in the calculator 383 times second function answer, and just copied that whole answer over. So that would look like this. I'll write it out. And so we're finding the revenue at this many units. And so we just put that whole thing in the calculator. And when I did that, I got 61,120 to the nearest cent, 42 cents. Okay, number 3, if in a monopoly market the demand for a product is P equals 175 minus 0.8x, and so notice this is a price equation, so price and quantity. So this is a demand function in this case. And the revenue function is R equals PX, where X is the number of units sold. What price will maximize revenue? So a bunch of words there. First thing is what will maximize revenue. So that means, again, we're thinking of an upside down parabola, and we're looking for the vertex. Next thing is what price will maximize revenue. So notice it's not asking what the maximum revenue is, it's asking what the price would be. So that means when we go back to solve, once we figure out where this maximum is happening, we don't want to know the maximum of the revenue, we want to know the maximum of the price. So we're going to have to plug back in that equation right there. And this equation is price. The price is dependent on number of units sold. But notice that isn't the same thing as revenue. Revenue is price times x. So to actually form the revenue function, we're going to go R of x, and this is just function notation. I could just also use plain R, but it's not saying R times x. 175 minus 0.80x. And then so that is our price. Again, the price is changing. Back in 1.6, it would be like, the price, they sold them for $50 each. So we went 50 times x. It's just like that. It's just now this is the price. And so it's like there's our price times x. And then distributing my x through, I get R of x equals 175x minus 0.80x squared. So this would be my revenue function. And so we want to know what price will maximize revenue. So we'll figure out what the maximum number of units is for the revenue, and then we can put that back into price. So now we're doing x equals negative b over 2a. So negative 175 over 2 times negative 0.8. And that makes rather unfriendly 109.375. And then just like in the last example, I'm just going to plug that back in now. But I'm not putting it into revenue because, again, I don't want revenue, I want price. So price will equal 175 minus 0.80 times that. And I got 87.50 when I did it. Okay, number 4. Suppose company has a fixed cost of $5,500 and variable costs per unit of 7/8x plus 1540. So just like in the last problem, how the price was a function, in this case the variable cost was a function. Back in 1.6, we're used to the variable cost being the slope. And so remember we did variable cost times x, and so say it cost $10 in labor and parts to make something, we did 10x, and then did plus fixed costs. This is going to be like this, except it's going to turn out quadratic. And then suppose further that the sell price is this X dollars per unit. So just like the last one, the price is also going to be a function. Form the profit function P of X from the cost and revenue functions. So remember from the first page, profit equals revenue minus cost. And so first thing we'll do is, right now we don't have either a revenue or a cost function. So we'll make each of those. And then once we do that, then we can make a profit function. So let's see, we'll do cost first. So our cost function is going to be fixed cost there, variable cost there. So variable cost is going to be times X. So that's just like back in the old equation, and then it'll be plus this. Let me go ahead and write that part down. So like in the old equation, we did the slope, which was the variable cost, times X, and then plus the fixed cost, which is our y-intercept. But this time, this is a function, so that means when I distribute, I'll get a quadratic because of the two x's. So cost will equal 7/8 x plus 1540, oops, sorry, that was squared, x plus 5500. And then we'll do the same thing and form a revenue function. So revenue is going to equal our price, this is our sell price right here, times x, because revenue is px. So 170 minus 8th x, and that's times x. So revenue equals 1700 x squared. So then to form our profit function, we're going to go this one minus this one. So profit will equal revenue and then minus cost. Okay, so then once I get all that written out, I just need to collect like terms. So this will be 1/8 minus 7/8, which would make negative 8/8, which would be negative 1 essentially, or negative x squared. And next we're going 1700x minus 1540x, and so that will be 160x. And then last we'll go minus that 5500. And so that would be our profit function. Okay, part B is find the maximum profit. So here's our profit equation that we just found from part A. So again, when we see maximum or minimum, we know we're finding the vertex. So this is going to be x equals negative b over 2a. So negative 160 is our b, and over 2 times negative 1. So that comes out positive and 80. And then once we do that, this says find the maximum profit. So this is x is 80 units. This is the number of units that maximize the profit, so I still have to put that back in here to get profit. So anytime we're looking for the actual money, we got to plug back in. So then profit will equal negative 80 squared 160 80 minus 5500. And then I just threw all that in a calculator, and I got that to equal $900. And then part C is what price will maximize the profit. Okay, so we know that there was 80 units is the number of units that will maximize it. And then back on this first page, we had further that the selling price of the product is this per unit. So this was our price equation, so I'll just bring that over here. So it's lowercase p for price, not capital P for profit. And then we'll put our 80 in there. And then just do that math, and then we get the price should be $16.90. Okay, so number 5 goes, the supply and demand for a product are given by these two equations respectively. Find the equilibrium quantity and the equilibrium price. So if we're looking for equilibrium quantity and price, we're looking for the P and the Q that satisfy both these equations. So basically what we have to do is solve the nonlinear system, which we're going to do by the quadratic equation in a second. So since P equals this and P equals that, that means they equal each other. So I'll take a second to write all that out. Okay, so there's my equations. I really should probably using lowercase q, but handwriting wise, capital Q works out better for me, so I'm going to do that. So now I want to do, since I'm trying to solve a quadratic, if we're trying to solve one, that means we're going to do the quadratic formula. So I'm going to add everything over to this side, and so I'll write that out here. Okay, so here's all that. I'm just doing the opposite to make this side 0. And over here I'll get 4q squared plus 2q, and then 16 minus 436 will make minus 420. And that equals 0. And so then if I wanted the numbers to be a little smaller, I could divide out a 2, and if I were going to try to factor it, I would do that. But again, I'm just going to throw it in the quadratic formula and let it do the work. So then we'd have q equals -2 plus or minus 2 squared minus 4, and then times a times c all over 2a. And then cleaning that up a little bit, I'm going to get q equals -2 plus or minus. So I just put all this in the calculator and took the square root, and that got me 82 once I did the root. And then over 8, and then adding those, and then subtracting -2 plus 82 would be 80 over 8, so that makes 10. And then the other one would be 84 over 8, or -84 over 8, but that's negative, and we couldn't have a negative quantity, so that doesn't make sense. So the -84 over 8, we know isn't viable with what the problem's about. So then once we have the 10, we need to go back, because this is the quantity, so we need to go back and find the price also. So I'll put it in the slightly easier looking equation. So price equals 10 squared plus 4 times 10 plus 16. And throwing that in the calculator, I got 156. So my equilibrium price is right there, 156, and my equilibrium quantity back here was the 10. Okay, section 3.1. So this was operations with matrices. So the first one we're doing is find the transpose of matrix A. And so the transpose, the notation for that was capital A for matrix name, with a little t up there for transpose, equals. And then when we do this, our rows become our columns and vice versa. So this first row becomes the first column. So -1 to -8. Second row becomes the second column. The third row, third column. And so that would be the transpose. Okay, for part B, we're going A minus B. And so I'm not going to write it all out. I'll just say what I'm doing and then write the answer. So we're going -1, and then we have to think of a minus right there. So minus -2, so it'd be -1 plus 2. So that'll make 1. 2 minus 4, -2. -8 minus 5, so -13. And then second row, 4 minus 3 would be 1. 3 minus -1 would be 3 plus 1, or 4. 6 minus 2, 4. And -3 minus 5 would be -8. 5 minus 3 is 2. 2 minus a -2 would be a positive 4. And then this next one, we're adding, but we're also multiplying by a scalar multiplier. So we're going to go 2 times equation B and then add to that 3 times equation A. And this one, I think I will write out equation, the 2B and the 3A right here. I'll cut away for a second and then come back and add them. Okay, so then I wrote out 2 times equation B. So this is just all of these values multiplied by 2, and then plus 3 times equation A. So same thing, it's just all these values multiplied by 3. And now I'll add those 2, and then that will equal this. So -4 and -3 makes -7, 8 and 6 for 14, 10 minus 24, so that's -14, 6 and 12 for 18, 7, 22, 10 minus 9, so that's 1, 21, and 2. Okay, and then this one is 3.3, which was Gauss-Jordan elimination method. So this is the bit with the matrices. And so at least in my class, I'm going to tell you, if you had me in person, to take these instead of reduced row echelon form, which would be the zeros all the way down and the zeros all the way up. On the test, I'm going to ask you to solve to row, just row echelon form, which is these lower zeros, and then do a back solve from there. So I'm just looking that you have sort of some semblance of how to work with the matrix. If you have a different instructor, they may want you to solve all the way down to reduced row, but again, I'm only going to ask for row. So the first thing I would do when I'm writing this down is swap out row 1 and row 3 so that I can get a 1 up here. So just as I'm writing it down, I'm going to go row 1, and I'm swapping that with row 3. So this will be 1, -1, 2, and 14. And then this will be -1, 2, 1, 6. And then this is my new row 3. Okay, so then next I'm going to figure out how to get my zeros underneath that first one. So if we do just, row 1 plus row 2 to make a new row 2, that will give me a 0 right there. And then after that, I will do -2 times row 1, and I'll add to that row 3, and that's going to make my new row 3. And I'll just do the scratch work over here and then put it all together. So row 1 is this, row 2, adding those, there's that first 0, 1, 3, and 20. So 1, -1, 2, 14, and then here's my new row 2. And then next I'll do -2 times row 1, which is, this is now row 1. So -2, 2, -4, -28. And then I'm adding to that row 3. So that gets me my next 0, -1, -5, -32. So that's here. And then this one came out pretty nice. So we already have, if I just do row 2 and row 3 together, it's already 1 and -1. Sometimes you would certainly have to do some more math to make these cancel, but this one came out good. So I will just do row 2 plus row 3 to make my new row 3. Okay, so I'm going to do row 2 plus row 3 to make my new row 3, and I just wrote out my row 1 and my row 2 already, and now I'll do that math. So 0 and 0 for 0, 1 and -1 for 0. Right here I get -2, and then over here I get -12. And so now what I'm going to do is I'll rewrite this as a system of equations on the next page. Okay, so here is the old matrix, and then here it is written with the x's, y's, and z's back in it. And really this isn't even row echelon form. I should really do -1/2 times this and make it a 1 and a 6. I'm just going to finish that math off right here. So -2z equals -12. And so then dividing, there's z equals 6. Once I have that, I can come back to the second equation and put in for z and solve for y. So 18 and 20, so bringing that over, y would equal 2. And now I can go back to the first equation and plug in for y and z and get x. So down to up 12 would be 10 equals equals 14, and then subtracting x equals 4. Okay, so here's the next example, and I swapped row 1 and row 3 again. Could have done row 2, just haven't picked. This one looked easy, nice and easy. And then just wrote out the augmented matrix. So now I'm going to do negative of row 1, and I'll add to that row 2 to get my first 0. And then after that, I'll do negative 2 times row 1 plus row 3. Oops. That'll make row 2. And then plus row 3 will make my new row 3. So, super easy equation to work with. Negative 1, negative 1, negative 1, negative 1, and 1, negative 3, 2, and 2. So we get our first 0 there, negative 4, 1, and 1. So we got 1, 1, 1, 1, and 0, negative 4, 1, and 1. And now I'll go negative 2 times this to knock out that 2 right there. So negative 2, negative 2, negative 2, negative 2, and then this one. So 0, negative 4, 1, 2. So that's my new row 3. And if you look at what happened, I got the same equation except the equal side is different. So this would make them parallel. If I tried to go and do, say, negative row 2 plus row 3 to make my new row 3, just to show what would happen, I would have 0, 4, negative 1, negative 1, and then this. And I get 0, 0, 0, 1. So that means 0 equals 1. So that is inconsistent. Or a no solution. And so if it comes out all zeros, that would be dependent. On my test, I wouldn't do that, but again, if you have a different teacher, they might. Okay, so in terms of review, I'm just going to do 4.1 and 4.2 together. 4.2 was basically just an extension of 4.1. And the way I have the problems written is a little bit different than you saw in the homework. What I'm trying to do is break up sort of different aspects of the problems into smaller problems. Because if you remember these, by the time we're seeing all the skills, it's like, it becomes like a 20-minute problem. And so I don't want test questions quite that long or that heavily weighted. So you'll see I kind of broke stuff up for mine. So this first one goes, company manufactures 2 kinds of hedge trimmers, one of which is cordless. The corded trimmer requires 2 hours to make. The cordless model takes 6 hours. The company has only 600 hours of work to use in manufacturing each day in the packaging department. It can only package 200 trimmers. The company makes a profit of $30 for the corded type, $50 for the cordless. And so we're setting up the constraint inequalities and the objective function and then not solving. So all I'm looking for here is to see if you can go from words to equations. So we're going to have x equal the corded, and we're going to have y equal cordless. And we have kind of 2 totals here. We have packaging was 200 hours and manufacturing was 600 hours. So we're going to have, for the first kind, we have the corded kind take 2 hours to make, and the cordless takes 6 hours to make. So we're going to have, excuse me, 2 times the corded plus 6 times the cordless, and then that has to stay under 600 hours because this is the most hours we have. And then in terms of packaging, we can only package 200 trimmers a day. So x of the corded kind plus y of the cordless kind has to stay less than or equal to 200. And then, so that's our constraint inequalities. And then I guess technically I should have x is greater than 0 and y is greater than 0. I'll probably forget to do that in class, but technically those should be there. This is really what I'm looking for though. And then find the objective function. So that's this last sentence. Company makes a profit of $30 for corded and $50 for cordless. So our profit is going to be $30 times the corded kind plus $50 for the cordless kind. And then from there, you know, I could solve, but in this example, we're not going to. So for the application problems, especially because the numbers come out kind of ugly in terms of graphing on a time test, this is as far as I'll have you take it. Okay, so this next one is the Well-Built Company produces two types of wood chippers, economy and deluxe. Deluxe model is 3 hours to assemble, half an hour to paint. Economy model, 2 hours to assemble, 1 hour to paint. The maximum number of assembly hours available is 18 per day, and the maximum number of painting hours is 5. The company makes a profit of $90 for deluxe, 65 for econ. So same thing as last time, set up the constraint equation, inequalities, and then the objective function. So I'm going to let x equal deluxe, and I'm going to let y equal the economy. And so the things that felt like totals were 18 assembly hours and 5 painting hours. So our assembly, the first one, let's see, deluxe took 3 hours to assemble, and then half hour to paint, so that'll be the next one. And the economy model takes 2 hours to assemble, so plus 2 times each economy one, and that has to stay less than or equal to 18. So that would be my assembly equation. And then for my painting equation, that has to be less than or equal to 5. And the first one, deluxe, took half an hour to paint, and then the other one took an hour to paint, so like 1y. So those are my constraint inequalities, and then for my profit function, that would just be P equals 90 times the deluxe and 65 times the economy. Okay, number 3 is find the corners, given by the big black dots, so that everyone's really clear on where they are. Use algebra to show work for credit. So I'm purposely leaving the scale off the graph. You can probably figure out the scale fairly easily once you figure out the intercepts, but I'm still looking for the work for these points. For this one, which is sort of my in-class example, I made it a little bit more complicated because I want to have a couple I can do as example and a couple for you to try. But on the test, I'd probably only have a couple of lines. So let me start up where x is 0, so I'll start on that corner. So if I know x is 0 here because we're on the y-axis, so looking at this equation, if x is 0, 2 times 0 plus y equals 80. So now I have this corner point as 0 and 80, which certainly gives me information about my scale that I'll kind of use to check myself as I do the algebra. This next point right here, so that's the intersection of these two equations. So I'm going to go the 2x plus y equals 80. And then the next one is x plus y equals 50. So I'm just going to multiply this one by -1. So negative x minus y equals negative 50. And that gets me x, those drop out, makes 30. Once I have that, I can plug it back in. So I'll do 30 plus y equals 50. So now I know y is 20. And that seems consistent. So this point is 30, 20. If you look at the scale that is on there, that does look like 3 units over, 2 units up, or 30 and 20. Again, this is the math I'm looking for. So right here, that looks like the 2 dashed ones. So the x plus 4y equals 80. Again, I'll just do the negative of this one. So negative x minus y equals minus 50. So x's drop out, 3y equals 30, and y equals 10. And once I have that, I can plug back in, and then x plus 10 equals 50, so x would be 40. So this point right here is 40 and 10. And then this last corner point right there, in this case, the y is 0, so x plus 4 times 0 equals 80, so x equals 80. So this one would be 80 and 0. Okay, so these are the linear programming from section 4.2. So this is where we have to do everything. But like I said, I'll use those other problems to see some of the other skills and then give you friendly things to graph so that this part of it isn't terrible. If you can read the corner points off your graph, and my intention is for you to be able to read the corner points off the graph, you can just do that, because I'm going to see that skill in another problem. So let me get these things graphed. I'll do this one in black. So x, y. If x is 0, y would be 4. And if y is 0, then 2 times 6 would make 12. And so I'll just do my scale, 2, 4, 6, 2, 4, 6. So x is 0, y is 4. Oops, and I mislabeled 4. That's not good. Okay, so x is 0, y is 4. That's right there. And then when x is 6, y is 0. Okay, and then this next one I'll do in red, x, y. So when x is 0, y would be negative 4. And when y is 0, x would be 2. So the problem is y negative 4 is not showing on my graph. So that's a little unfortunate. So let's make up another point. How about if I need that to come out 8, so why don't I make x 3? And then, so then 12 minus 4 would make 8, so then y is 2. And that will get me something on my graph I can graph. I could draw this further and just do little hash marks, but I just thought I'd grab another point. So when x is 2, y is 0. And then when x is 3, y is 2. And so I'm getting a line that looks like, oops, that. And then we also have x greater than 0 and y greater than 0. So that's going to keep us in the first quadrant. So we get this. And sorry, my graph's a little messy there. But so once I get those graphed, now I can find my corner points. And so I have one here at 0, 0. And then I have one here at 0, 4. And then this one, if you draw it on paper not using a Sharpie and a ruler, you'll be able to read that it's 3, 2. And the last one down here is 2, 0. And I guess I didn't point out, these are less thans, and so that means it's going to be the kind that's bounded. So it's going to be that region right there. And then all I have to do is put these into the objective function and figure it out. So for this one, f would be 0. For 0, 4, f would equal 12. For 3, 2, if we put that in, 12 and 6 would make 18. And put in the 2 and get 8. And we are trying to maximize this. So our maximum is 18, and it occurs at 3, 2. Okay, so for number 2, we're going to minimize that function with these constraints. And so scale-wise, I'm going to count 2, 4, 6, 8 on these. So that would be 4, 8, 12, 16, 20. Okay, so for this first equation, that one's pretty friendly. When x is 0, y is 9. When y is 0, x is 9. So that's going to be basically there and there. Okay, and then the second one I'll do in red. X, y. So when x is 0, y would be 5. And when y is 0, x would be 15. So x is 0, y is 5, is right there. And then 15, so that's 14, 15 is right there. And this last one I'll do in blue. So when x is 0, y is 12. And when y is 0, x would be 3. So 0, 12 there, and 3, 0 would be right here. Okay, and this one, these are all greater thans. So that means 0 would fail in all those equations. So that means we're going to shade the unbounded region. And then we, of course, have the x and y axis. So out here is what we're looking for. So our corner points are going to be there, 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 and there. And so On the test, you'll have a little graph, and you can use a straight edge, not a big old Sharpie. So you should be able to read the two intercepts off the graph, and they're also on this table. So the y-intercept for the blue one was 0.12. Actually, let me start a list right here. And then for the red one, the intercept was at 15. Again, on the test, I will make this something that you can read off of there. So it's a little tough with the Sharpie. If I solve the system, I could do the black one and the blue one together. So that will be 4x plus y equals 12, and I'll do the negative of this one. Oops, that should be a y. So then 3x equals 3, and x equals 1. And then plugging that back in, I get when x is 1, then the y would have to be 8, because 1 plus 8 makes 9. And then I could solve the black one and the red one together. So I'll just do x plus 3y equals 15, and then do the negative again. And that makes nothing there, 2y and 6, and so y equals 3. And so when y is 3, plugging back in here, then the x would be 6. So there's my corners. Again, I don't think on this problem I would try to make it where if you draw a decent line, you'll be able to read it. This one, the scale was a little bit big. And so then we just put these into F and then figure out which one comes out the smallest. So for this one, F would be 24. For 1/8, F would be 21. And then for 6/3, F is 36. And then for 15/0, F is 75. And this one we wanted to minimize, so that minimum's right there at 1/8 with a value of 21. Okay, and finally we have section 4.3, the simplex method. So this is the one that had so tons of definitions with it and lots of steps. So if you want a little slower version of this, definitely go back to the original video that I posted for the section. In this one, since it's a review, I'm not going to go through all this. I'll kind of talk through the steps as I'm doing the problems, but I'm not going to sort of redefine everything. So if you want sort of a broader explanation of this, do check out the original video. So question 1, we have use the simplex method to maximize the given function. Assume all variables are non-negative. So that's what we're maximizing, and then these are constraints. So the first thing we do, for kind of going down those steps from the first page, is create slack variables to convert the constraint inequalities to equations. So what that would look like is this one will be x plus y plus my first slack variable equals 4. And then this one will be 2x plus y plus a second slack variable equals 5. And then step 2 is to write the objective function, that's this one, equal to 0 with the terms involving variables as negatives. So that means we're going to keep f positive and we're going to bring these over. So this would look like negative 3x minus 4y and then plus f equals 0. And step 3 is to make a simplex tableau with the constraint equations, these guys, in the upper rows, and then the revised objective equation in the bottom row. So I'll set that up now. Okay, so here's my simplex tableau with, here's the first equation, the 1, 1, first slack variable. This will be S2 and this will be F. So here's my second equation with the first slack variable missing, second one filled in, and then the objective function down here. So this is our F column. So now that we have that set up, Next thing we have to do is select a pivot column by finding the most negative entry in the bottom row. So we look in the bottom row, -4 is our most negative entry right here. So this is going to be our pivot column. Step 5, select the pivot row by dividing the last column, this one, by the corresponding row. And then the smallest positive result is going to be the pivot row. So here we'd have 4, this divided by 1 would be 4, and here we have 5 divided by 1, which would be 5. So the smallest positive result would be the 4. So that makes that our pivot. So number 6, find the pivot. There we go, it's right there. Divide the pivot by itself or multiply it by the reciprocal if it's a fraction. So basically, if this isn't already 1, I'm going to divide to make it 1 or multiply to make it 1. And then I'm going to use that 1 to obtain zeros below it. So now we got our pivot, and we're going to use this to knock out that 1 and that 4. So first thing I'll do is I'm going to go negative of row 1, and I'll go plus row 2, and that's going to make my new row 2. So that'll give me a 0 right here. And then I'm also going to go 4 times row 1 plus row 3 to make my new row 3. So if I do a 4 across there, I'll get positive 4, negative 4. So I'll get that set up. So this one's going to be negative 1, negative 1, negative 1, 0, 0, and negative 4. And we're adding row 2 to it. Okay, so we do that. We get 1, there's the 0, negative 1, 1, 0, and 1. Next we're going to go 4 times row 1, so multiply all that by 4. So 4, 4, 4, 0, 0, and then 16. And we're going to add to that row 3. So here we'll get 1, there's the 0, 4, 0, 1, and 16. And so I'll move to a clean sheet of paper and rewrite the simplex tableau. Okay, so here's the new simplex tableau. I just took the original row 1 and then the new row 2 and the new row 3 and put them in here. So step 7 is if all the indicators in the bottom row are positive, which in this case they are, we go on to step 8. If there are still negatives, we'd have to go back and repeat steps 4 through 6. Step 8 is set all the non-basic variables to 0 and the basic variables and the objective function from the rows of the matrix. So what that means is, so remember the basic variables are the columns containing 1s and 0s. So right here, I'll just put a little dot above it. Actually, I'll label it. How about Y? This was S2, and this was F. And so those are the ones that are the 1s and 0s. So what that means is, so this is non-basic, so we set those to 0. So X is 0. Y, that's right here, is 4. This was S1. This is S2. S1 is 0 because that was non-basic. S2, that one is 1. And then F is 16. So it's maximized at 16.